Hello, my name is Mary Lou and this is my Lab 2 on projectile motion. Our purpose is to observe and analyze the motion of an object moving in 2 dimensions under the influence of gravity, and compare it to computational models. One model includes only gravity, while the other includes both gravity and air resistance, which is drag. The goal is to compare the predicted and actual trajectories over time to better understand how drag affects real-world motion. Our preview of main result is that the computational model that includes air resistance more accurately represents the motion observed in tracker compared to the model that only accounts for gravity. We have our important models and fundamental principles that we'll be using. The first one is the velocity update formula, which will be able to tell us our updatable velocity given those terms. We also have the position update formula that allows us to find the updated position based on those terms. We have force of gravity equation and its vector, which is given by 0, negative mg 0, indicating we're pointing in the negative y direction. And we have the drag force given by negative b times the magnitude of velocity squared times v hat, where negative b is the proportionality constant. Our system is the paper ball, and our surroundings is everything else, such as air and force of gravity. And this is how we can derive momentum and velocity update formula from Newton's second law and our position update formula. So our procedure is to film a video of an object, wadded up paper ball, being thrown as a projectile, import the video to tracker, and track the position of the golf ball at each time frame as our observed position. We use GlowScript to create a computational model of the golf ball being thrown for t seconds to create predicted position by editing the starter code. Plot the data of position over time created both computationally and experimentally to compare the outcomes of the experiment. This is the video of the observed position of the crumpled up paper being dropped above my head, which took around 19 points. As you can see on the graph, there's time in the x direction as well as time in the y direction. When looking at our data points, you can see our initial and end time, which was 0 to 0.633 seconds. Our initial position, which you can see there, helps us calculate our initial velocity. Using our final position, which was at 0.007512, negative 1.699, we can subtract initial position from final position and divide by time to get our initial velocity. For the computational model, I changed the ball's mass to 14, which is in grams, as well as the ball's position and velocity vectors to match the ones I got. I kept the delta t to be 1/30 for the size of each timestamp. The drag coefficient is the b factor from the drag force equation that can be manipulated to see the outcome. Then this is the drag equation put into code, as well as the gravity vector, which was our earlier vector of 0, negative mg 0. We can calculate Fnet using F gravity and F drag, and we can use previous code of calculating ball velocity and position using Newton's second law. Below all of that is the code to generate the arrows for gravity and drag. So this first one, b equals 0, is when drag coefficient is 0, so there's no drag. As you can see, this is an ideal prediction of a projectile motion. There's only gravity being affected, making linear and sort of parabolic. When b is equal to 1, meaning a small drag coefficient, it affects the model, but it's not too big of a difference. But the drag does have an effect. And for b equals 5, you can see the arrow is much bigger, and from what we can tell, it has a much bigger impact on the model as a whole. We can see the position x over time goes from being quite linear to pretty parabolic. So these two top graphs are the computational model where there was no drag, an ideal situation, and on the bottom is our experimental data that shows that it's not ideal, which basically means that there's other forces acting on the projectile than gravity, which is where drag comes into play. Possible errors that could have been that could have caused the discrepancies in the points of could have been the points of mass on the paper. Could have been rounding errors or outside forces like drag and friction. Finally, the what ifs and whys. Do any of our models predict terminal velocity? The first graph, which is time versus velocity in the x direction, does predict terminal velocity, and the second one that goes in the y direction does not, because it is a non-constant velocity. Is the net force really 0? Projectile was given by 2 times the initial velocity sine theta over g, and if you throw it straight up, it's going to be 2 times v initial over g. This essentially means throwing an object in a projectile path takes less time to hit the ground than throwing it straight up with the same speed. since going straight up means it has to go all the way up and then come all the way back down. Thank you.